Oh, what the? Hey, Kev, wake up! This one's important. He's gonna do some examples, eh?
Yes, folks, Jono's right. Lecture 9 is entirely about examples. So we've just spent a whole part of lectures building up Lagrangian mechanics, and we've used it on some rather trivial problems that doesn't really point to the power of the approach. And there's not much point having a tool and not really knowing how to use it. So today what I want to do is spend the entire class doing problems, and I'm going to do 3. I'm going to do 2 problems in the first half, 1 in the second half. They're going to go up in difficulty, and the importance of having a Lagrangian approach. The first one you can kind of do with a Newtonian approach. You've probably done it in first year. If you haven't, you should. And the other 2, I'm not going to do it via a Newtonian approach because I know how painful it is, but I'll let you do it if you want to, just for a challenge. So without wasting any further time, let's get to the first problem. First problem is classic first year mechanics problem called Atwoods Machine. And so what we have is a pulley on a frictionless bearing, and there's a string running over the pulley with 2 different masses, M1 and M2, connected to opposite sides of the string. Okay, and what we can do here to make the problem easily addressable is to define a 0 for a coordinate system just here, with a length x, which is the position of mass m1 below that pulley point, and a distance y, which is how far mass 2 is below the same pulley point. Okay. Alright, so Lagrangian approach. I like to do this sort of running by a formula. Sometimes I break my own rules when I'm solving problems because it might be obvious that I can skip a step, but today I'll try to hold to them all. So the first one here would be to work out the degrees of freedom. The problem is kind of set up to make you think that there's 2. There's an x and a y in here. And in a Newtonian approach you might want to keep the 2. But what you quickly realize here is that for every change in this length x, there's going to be a corresponding change in this length y, and it's going to come from a constraint, and that's the next thing we're going to think about. So really there's only 1 degree of freedom in here, which is just essentially rotation of the pulley at the top, because it mediates the motion for everything else in the system. Okay. The second one is constraints, and the constraint in here is essentially the string, right? What it means is that there is always going to be some relationship between this position y and this position x, such that m1 and m2 can't go wherever they want. They have to be put in such a way that they're still connected by the length of the string running over the top of the pulley. Okay. At this stage, we're really just thinking about the problem, and it's part of the reason why I like to have this step, because too many students, when they do exam problems, and in lectures like this I actually often like to talk about exam tips, launch straight into the problem without actually stepping back for a second and going, what's going to be my plan for solving this thing? What are the things that are obvious to me right now? Okay, so we have a constraint, and we can already write this constraint down. And it basically is that the length of the string L is going to be equal to our distance x plus our distance y plus pi times the radius of the pulley. Okay, so really the length L is going to be all the way up to here, the half the circumference of the pulley plus this distance x. Okay, now one of the things you can do sometimes, particularly if you've done enough problems, you can spot where you can cut these things off. We know that some bits of this are going to be baggage, right? L, it doesn't really matter how long L is. You know, if we lowered these 2 masses down or raised them up a little bit, it's probably not going to change the way the problem works. And also the radius of the pulley is probably not going to matter here, okay? And so what we can do is write this thing instead as y is equal to minus x plus a constant. And really what we're doing here is just putting a restriction or a relationship between y and x in this problem that takes what would have been two coordinates, y and x, and now turns them into one coordinate, which makes sense because we have 1 degree of freedom, okay? So we already spot that we've sort of set this problem up right. We also know a couple of other things in here. One is that because these are connected by a string, the speed that this goes down will be equal to the speed that this goes up. And the acceleration that this goes down will be equal to the acceleration that this goes up. And you can get that basically by taking the derivative of both sides of the equation we just got, right? So what we would have in here is essentially y dot is equal to minus x dot, and the derivative of a constant is 0. And if we take a derivative again, y double dot is equal to minus, sorry, that should be x double dot. Like so, okay? So sometimes you can pull a couple of equations out from a constraint that are useful later on. I wouldn't spend forever trying to pull them out because sometimes they're not useful, but a few seconds just teasing out a couple of relationships can actually be really handy in solving the problem. Okay, so now we get down to business. We want a kinetic energy, we want a potential energy, we want a Lagrangian, we want to get Euler-Lagrange equations, solve them, get a meaning out the end, right? That's the full list. So first thing we're going to do is kinetic energy here, and the kinetic energy in this problem is not too hard. It's going to be the velocity attached to m1, the velocity attached to m2. We don't really care about the pendulum, and we don't really care about the string because it's probably defined as being massless, and the pulley's massless, and all the idealities of the problem make those things go away, right? So this is a half m x dot squared plus a half m y dot squared. And of course we've got two masses, so we've got to work out which one's which. So this will be mass 1 and this will be mass 2 just over here, okay? But we know in here that y dot is equal to minus x dot. And so that means that y dot squared is equal to x dot squared. And so we can pull these terms together, and what we get is a half m1 plus m2 x dot squared, okay? Really simple expression in here. Next step in here is to get the potential energy. Today I'm going to call it U. It's going to be essentially the height, because we're dealing with a gravitational problem, the height of our mass below whatever our origin is going to be, okay? So the potential energy here will be minus m1gx minus m2gy. And of course, here we've got minus m1gx minus m2. We can use our constraint equation in here. So this will be, sorry, there's a g just there, minus x plus constant. And so this thing, we can pull the terms together. This will be minus m1 minus m2 gx plus a constant. Okay? Now some of you will be going, what's he doing with this constant thing? I don't really care what it is, and the reason why I don't really care what it is because whenever I use t and u in Lagrangian problems, I'm never actually using the Lagrangian, I'm using derivatives of the Lagrangian. And so any terms that are constant in t and u are going to get taken out when I do derivatives. So this is why I don't care about them. I can just turn a constant into a constant into a constant, and later on it'll just disappear on me, okay? It's one of the nice features of Lagrangian mechanics is often constants you don't really need to care about. So here's our Lagrangian, L equals t minus u. And so it will be a half m1 plus m2 x dot squared plus m1 minus m2 gx, okay? And we can drop the constant here because when we take the derivative it's going to go away, right? If you're doing this as an exam problem, it is probably worth a couple of words just noting drop the constant because it will not carry through the derivatives or something like that, just so that someone knows that you know why you dropped this thing. But it's okay to just dump the baggage. Okay, so there we go. Lagrangian pops out nice and neatly. Next step here, we want Euler-Lagrange equations, and we're going to see one of the nice features that came up in yesterday's lecture, which is that if you can reduce the number of coordinates by knowing about constraints and degrees of freedom, you get fewer Euler-Lagrange equations to solve, right? And in the ideal case, you only get one, and here today we've only got one, okay? So, getting our equations of motion, it's going to look like this. dl on dx is d on dt, dl on dx dot. And of course, as you remember yesterday, the term on the right, just here should be the momentum, and so it's the one carrying the dot, because you add a dot to the f to get a p. Okay. All right. So we can take these two derivatives in here, and they're fairly easy, right? dl on dx is going to be, there's only one term in x up above. It's m1 minus m2g. dl on dx dot is going to bring we're going to bring the 2 up here down to knock out the half, and so it's going to leave us with m1 plus m2 x dot. And so what we're going to have here, if we build this all together, is m1 minus m2g is equal to d on dt of m1 plus m2 x dot. And then, of course, the mass is time dependent, so the only thing we have to take the derivative of here is x dot. So it's going to be m1 plus m2 x double dot. And then we just got to clean this up to a final term, right? We can see the solution is very, very close and easy to get to here. So it's x double dot is equal to m1 minus m2g on m1 plus m2, like so, okay? And if you do this via Newton's approach, you'll get exactly the same answer. Some of you will recognize this from first year. The reason why we like to teach you about Atwoods Machine is because it was one of the early ways of measuring the acceleration due to gravity, right? Because if you look at this equation for a moment, this term at the top is m1 minus m2, and if you make m1 very similar to m2 but not quite exactly the same, that becomes small, and so your pulley essentially down reduces or down converts your acceleration due to gravity to a more manageable acceleration that you can actually measure. And so if you know those two masses accurately and you can measure that acceleration due to gravity, which might be, you know, 0.1 meters per second or something, you can then use the knowledge of the mass relationship to get g. Okay, it's a really nice experiment for doing this. The reason why it becomes tricky is that very hard to get frictionless pulleys, very hard to get massless pulleys, and it's very hard to get perfect strings, right? So it works, but it's not the best way to measure acceleration due to gravity. The other thing that you will notice is that we solved this problem and we never had to deal with the tension in the string, right? It never came up. And if you go back and do the Newton's version of the problem, you actually really do have to deal with the tension on the string in order to solve this problem. You also have to make a decision about which way the system is going to travel in order to solve the problem as well. So this is one of the nice features of Lagrange equations that I mentioned in the last lecture, is that it basically makes the constraint forces go away so the problem becomes a bit nicer and easier to work with. Okay, so that's the first one, kind of easy. Gives you an example of a Lagrange equation approach that maybe isn't radically easier than the Newtonian approach, because the Newtonian approach you can do in an equivalent amount of algebra. They're probably about equal, and given the choice of which one to do, I'd probably take the Lagrangian approach just because it's easier to do and there's less mucking around with tensions and components and stuff like that. But you can do them either way, and neither's harder than the other, okay? Alright, so the second problem I want to do, and we'll take a break after this one because this is kind of a substantive, meaty problem, and then the last one we'll do is actually a really properly hard one, so it needs a good half an hour or so. is what I've taken to calling the Slidey wedge problem. Okay, so what we have is a frictionless surface just here, and we have a triangular wedge sitting on it with a mass big M and an angle alpha in the corner, and it has frictionless surfaces as well. So we could imagine these are made out of ice, for example, and we're in an environment where the ice surface is wet, so it's nice and slippery. And on this triangular wedge, we have another mass, little m, that we put right at the top here, and we set this system up. So we set our triangle up, we set a little weight block at the top, we make them stand still for a second, and then we just let it go. And what we want to do is work out how long it takes for the little block at the top to slide to the bottom of the triangle, okay? This one, with Newtonian approach, gets messy really quickly, and it gets messy really quickly because there's a normal force you have to worry about here, and then there's a normal force you have to worry about here, and then you've got balances of all sorts of normal force components, and the whole problem becomes a little bit ugly. I'm not going to do it. I'm going to let you do it for yourself if you really want to try it. It's a good exercise as an undergraduate. I never have to solve mechanics problems for exams anymore, so I just avoid the pain. I had to do it way back ago, and I remember how horrible it all was. And so we have a coordinate system that we've set up here. We've kind of conveniently set it as x in this direction and y pointing downwards. Sometimes this is one of these things in problems where the person setting up the problem just gives you a coordinate system so they don't have to drive themselves crazy trying to work out what's going with all the minus signs when they mark it. And they've also given you some advice on what the general coordinates should be. Okay, and so you'll remember in yesterday's lecture we talked about our generalized coordinates qi, and our Cartesian coordinates are alpha, which would be like x, y, z. And you can see this is one of those problems where we are going to interchange between the two, right? We have an x and y, which would be our r alphas, and our q1, q2, which is basically just the position of our triangular wedge from some fixed point. And if you think about, you know, how this is probably going to work, this block sliding down the top is probably going to push this wedge to the left, and so this Q2 is kind of designed to be some fixed point out here so that we don't go sliding off into negative values, okay? So again, sometimes there's really subtle hints in the way that problems are set up that kind of guide you into the thinking a little bit, okay? And then of course, our Q1 up here is designated from the position that we start, which kind of makes sense, okay? Big advice on this in terms of exam technique is to be careful about it, because sometimes you can be fooled, but sometimes there's things you can read into problems just by thinking about how the problem goes together. Okay, so degrees of freedom. There's two, and one for each of the two masses, right? The wedge can go left-right, so it's got a positional one, and it's the thing Q2, so it's kind of been given away to us. And then the little mass M up the top here can slide along that block, so it's got 1 degree of freedom, and it's already been assigned Q1 for us, okay? So the person setting up the problem has kind of given us the answer to this bit already. Constraints. The only constraints in the system really are that there's 1D motion, right? The wedge is 1D, the mass is 1D, and there's nothing else really that we can see in here that's going to help us in terms of constraint equations, okay? So at this point we might as well kick straight on. Someone's done part of the problem for us. We have a Q1 and a Q2, and they're the coordinates we're going to run with. And so what we want here is Lagrangian. The kinetic energy is going to have two components, right? One's going to come from the mass big M, one's going to come from the mass little m. And we need to do them separately. And the mass big M is the easy one, and it's the easy one because of reference frames. And I know we haven't done reference frames in a lot of detail yet. They're coming up in a lecture or two from now, but it's easy enough to explain. We've got the reference frame of the observer, right, in this case, which is just us sitting there watching this scenario unfold. And for us, a fixed position here makes sense, and so M is measured relative to that fixed position, and so everything behaves itself sensibly in terms of big M. The trouble comes when we deal with little m, and it comes because our coordinate is registered to a to something that is potentially moving and or accelerating, right? So in a sense, the reference frame that we've set up in this problem for little m is not the same reference frame as big M, and so what we've got to do is hook those two reference frames together, okay? But let's do big M first. So big M is really easy. Let's call it T big M. It's just going to be a half times the mass big M times Q2 dot squared, okay? So it's just a half mv squared for the big block. It's really easy. We pop that one straight out. Little m is trickier, and that's because we know the velocity of little m very, very easily relative to the big block, but then what we've got to do is convert that into the same reference frame as we're dealing with the big block, right? And so there's going to be two motions. There's going to be q1 dot relative to big M, and there's going to be the motion of M. And so what we can do is basically rely on vector sum, right? So the velocity of little m is going to be its velocity relative to m, big M, and big M's velocity, and we just add them as a vector sum, right? So this is fairly simple to do. V little m is going to be, and we just, before I write this, I'm just going to draw a little diagram because we need to sort out some of our trigonometry here. We've got a system like this, and I'm exaggerating a little bit just to get some emphasis in here. We've got our little block, little m on here. This component just here, if we think about this triangle, this is the adjacent to this angle, this is the hypotenuse, so everything happening in this direction is going to be cos, right? So this will be a cos alpha component, and then everything that's going to happen in this direction, this is an opposite, this is a hypotenuse, is going to be sine, okay? Boom. Sine alpha. And when I was an undergraduate, I'd usually set this up in my mind or on a scratch piece of paper somewhere right at the start of the problem. I would work out what my horizontal components were going to be, and I'd just write down horizontal is cos and vertical is sine, and then I just know all the way through the problem which way things are going to go, right? Okay, so we've got v little m, and it's going to be, now we're going to, we know from yesterday's lecture that we can convert our generalized coordinates to our Cartesian coordinates, and we can convert our Cartesian coordinates back to our generalized coordinates, and as long as neither of those two things has an explicit time dependence, everything's okay, right? And there's not going to be an explicit time dependence here, it's all okay. What we can do in here is now turn this motion into x and y so that we can hook on to what's going on, okay? So if we think about the x component here, there's going to be a q1 cos alpha in a horizontal and a q2. So it is going to be q1 dot cos alpha plus q2 dot. And we add those two because q2 goes in this right direction, q1 goes in this right direction. So once we translate this by the angle, we've got two things that add together, with positive being to the right, okay? And then my y direction, I don't have to worry about this block because it's constrained on a plane. It's not moving up and down. This one is, and so it's going to be q1 dot sine alpha. And of course this is, we could call this vx and vy, right? Okay, and likewise we could convert back later on from vx, vy to q, to our q1, q2 system, okay? All right, so now we've got something we can play with, and we can get our t little m, and so our t little m will be a half m vx squared plus vy squared, okay? And so now we're just dealing with the little block, If I wanted a velocity for the big block, I could call it big V, for example, but then I might get confused with potential energy. One of these tricky things with variables. Don't introduce them unless you need them, because otherwise you can get yourself into trouble. Okay, so it's a half m. This is going to be q1 dot cos alpha plus q2 dot squared plus q1 dot sine alpha squared. We can work our way through and do everything we need to in here in terms of squared. This is going to be a half m q1 dot squared cos squared alpha plus 2 q1 dot q2 dot cos alpha plus q2 dot squared plus q1 dot squared sine squared alpha. Okay, and you'll notice straight up here, this term here and this term at the back are going to give us a sine squared plus cos squared equals 1 term. Okay, so this thing is going to end up being a half m q1 dot squared. We can next grab our q2 term from there, so plus q2 dot squared, and then we got a mixed term on the end, 2q1 q2 dot dot cos alpha, quite nicely. Okay, and so all we've used is just cos squared plus sine squared equals 1, right? Okay, so now we can push on ahead. A lot of the hard work has been done in setting up this problem now. Our total, wrong color, our total kinetic energy, T, is going to just be Tm plus Tm. And so what we're going to have here is a half big M q2 dot squared plus a half m q1 dot squared plus a half m q2 dot squared plus m q1 q2 cos alpha, and I've got to not forget the dots there. Okay, we can cluster some terms in here just to make things nice and easy, and what we're going to do is we're going to cluster the q2 dot term, square term out the front. So it's going to be a half big M plus little m q2 dot squared plus a half m q1 dot squared plus 2q1 dot q2 dot cos alpha, just in here. Okay, and I guess what the reason why you would do that clustering at the moment might not be completely obvious. Okay, this might be one of these things when you come back around the question, you would spot that that would be the sensible way to do it. In an assignment, you would definitely do it in your final draft. In a exam, you could probably stop at the line before and just keep rolling, right? There's much more limited time in an exam. We also need our potential energy, and the potential energy for the big wedge is a constant, right, or zero. We can just ignore it because we're going to take derivatives later on. So we can ignore this term. The one that matters up here is going to be this one, right? And it's going to be mg times its height above wherever, and it's going to be our q1 projected onto the y-axis. Okay, so we can get this one pretty simply. It's basically just going to be minus mg q1 sine alpha, okay, where q1 sine alpha is just the position component along this direction. Okay, and we're basically deciding that our zero is where we start at the top, because we could add a constant onto that and the constant would go away. Okay, so then we got our Lagrangian, and in a lot of problems getting the Lagrangian is the hard part of the problem. We got a half m plus m q2 dot squared plus a half m q1 dot squared plus 2q1 q2 dot dot cos alpha plus mg q1 sine alpha. And just a little exam technique point in here. If I was doing this in an exam, this line here I wouldn't have done back up there because I would know that I can do it at the next step when I write down my Lagrangian. So I probably would have cleaned that up when I got to here instead, just to save myself some time. All right, so hard work done. Now we've got to deal with our equations of motion. And in this particular case, we've got 2 degrees of freedom. So we're going to have 2 Euler-Lagrange equations to deal with. And usually what I like to do here is, particularly if it's an exam, is work out which of the 2 is probably going to be the easiest and do that one first because I can just bank some marks, okay? And so it's going to be pretty obvious that the Q2 one is the easier of the 2 here, simply because it's the block where we didn't have to break up into components and stuff. So we'll do Q2 first. We need our derivatives. dl on dq2 is obviously 0 because there's no terms in it. And again, this is another way you can spot it. You can look at what the terms are in there, spot if any of the Lagrangian derivatives are going to go to 0. If they do, it's probably the easier of the 2 equations to solve, okay? dl on dq2 dot, of course there's terms in that, so we're going to carry the 1 up the front, m plus m. The 2 is going to come down from the square and knock out the half. And then we're going to have a term from the mixed term on the end, right? So this is going to end up with a plus little m q1 dot cos alpha. Okay, and just to make it clear, it's that term that is this one on the right, not the other one, okay? The 2 has knocked out the half, and the Q2 dot has disappeared by taking the derivative. Okay, so what I'm going to have here is dl on dq2. Sorry, 2's in the wrong place. 2 is d on dt. dl on dq2 dot. And I can spot something straight up here. Because this derivative on the right here is 0, I can automatically integrate with respect to t. And so where I'm going to end up with is big M q2 dot plus little m q2 dot plus m q1 dot cos alpha is equal to a constant. And if I was doing an exam, I'd put a little note in there, that's what I've done, right? Substituting in, I'm going to integrate with respect to t, and then this is my equation that pops out here, right? We can call this 1 because it's going to be kind of important going on later. And we want to attach a meaning to it. It's actually pretty obvious what its meaning is straight up here. It's basically just conservation of momentum in the x direction, right? Because there's a contribution from big mass to Q2. There's a contribution to little mass and its motion in the Q2. And there's a contribution in the cos component in here. Okay, so we're basically just adding up all the little possible components that we would have in terms of this. And the one thing you'll spot is that this mixed term mq2 is basically the motion of m because it's on a block that's moving, okay? All right, so Q2's out of the way. Let's deal with Q1. And one thing I'll just note for a second, me putting down that that's conservation P of X is probably not so important there. I pointed it out here just so that you can see that it actually does have a meaning, but in an exam I'd probably just keep trucking right on through to find the answer and come back later to explain what it means, unless I got stuck, in which case I'd try and finish off the problem by explaining what things mean. Okay, so our Q1 equation, we got 2 derivatives, and dl on dq1 is going to be, let me go back far enough I can see my Lagrangian again. It's going to come from this term on the end here, right? So we're going to have mg sine alpha. And then dl on dq1 dot is, I'm now going to take derivative of my q1 dot terms, and of course they're all clustered over in here on this right hand side, right? So I'm going to have a mq1 dot, because the square is going to drop out the half, plus the 2 is going to knock out the half, my q1 is going to vanish, and I'm going to have mq2 dot cos alpha in here, okay? And so you can already see why I chose q2 first, because it had one of the derivatives go to 0, so the equation's easier to solve. We're going to have dl on dq1 is d on dt, dl on dq1 dot. And some of you will be going, why does he keep writing his Euler-Lagrange equation all the time when he knows that it is? Basically, it's a hangover from exam technique. I want the examiner to know that I know some point in here, so that if I have an epic fail from this point onwards, I at least get part marks for demonstrating that I know the next step in the approach, right? Without having to write heaps of words to do it. So we can substitute into this thing. This is going to be mg sine alpha is equal to d on dt, mq1 dot plus mq2 dot cos alpha. And so this thing is mq1 double dot plus mq2 double dot cos alpha. And the reason I can take that derivative so simply is that I know that the mass is not going to change with time, this mass is not going to change with time, and this angle is not going to change with time. So the only thing that changes is q, right? I'm mentioning this right here because in the next problem, we have to worry about that as well, okay? So it's good to know what things are constant so you don't have to worry about them when you're taking derivatives. And for the moment, let's call this equation 2, just so that we can keep track of it. Okay, so what I'm going to do is go back to equation 1 now, because I can kind of spot that it's going to be useful to me, but in a slightly different form. And I'm going to take equation 1 and take the derivative with respect to time, right? So if I do that, I'm basically just undoing what I did up above. So it's going to, don't know why that changed color, but it did. I'm going to have big M Q2 double dot plus little m Q2 double dot plus MQ1 double dot cos alpha is equal to 0. Okay, so I've kind of just undone the thing that I did to get 1. What I can do here now is cluster some terms. So I'm going to cluster my Q2 terms. So this will be little m plus big M Q2 dot double dot. And I'm going to carry the other term on the other sides. This will be minus m Q1 double dot cos alpha. And then I can isolate my Q2. Because you'll notice that back up where I had equation 2, up here, I've got term in Q1, I've got a term in Q2 double dot, and if I can substitute something in from the other equation, I've got 2 equations to solve 2 unknowns, right? Okay, so this is going to be minus m on m plus m. I should have bought a packet of M&Ms to eat while I did this problem. Q1 double dot cos alpha. Okay, and we can substitute this into 2. All right, so now what we've got is mg sine alpha is mq1 double dot plus m minus m on big M plus little m q1 double dot cos alpha on the end here. Okay, so that's just doing that substitute straight in. The one thing we can note in here is that we can cancel out the little m's right through. So let's get rid of those 3 straight up. Okay. The next thing in here is that we can pull the Q1 out the front. So G sine alpha is Q1 double dot there's going to be 1. The minus inside here will come out to there, so this is going to be a minus just here. And then we're going to have little m, we've got a cos squared alpha now on big M plus little m, like so. Okay, and what we're interested in is Q1 double dot, right? So now we need to kind of flip this equation around. So Q1 double dot is equal to G sine alpha on big fat fraction here, 1 minus m cos squared alpha on big M plus little m. Let's put this in brackets here. Well, that bracket's too big. Bracket just there. There we go. And of course, if you have a look at this thing, you'll notice that alpha's a constant, g's a constant, m's a constant, and m's a constant. So this thing actually is just a constant. We know exactly what it is. We can put all the numbers in, but we know this thing is a constant in the end. And so what it's telling us is the acceleration down this slope is a constant. We would kind of expect that, right? It's falling under gravity, but we know it's not going to be g. And now we've teased out exactly what that is, okay? And so the last step we have to do here is solve the actual problem. And so this is one common pitfall in exams. People get excited about where they've got to, and they haven't bothered to read the problem and go, have I answered the problem that was asked? Okay, it's usually worth a couple of marks here. How long does the block take to reach the bottom? Okay, so we're going to do it. It's a little tiny piece of Newtonian mechanics. We know that the time to get to the bottom of that slope, it's starting at velocity equals 0 at the top. So the distance down the slope at t is going to be a half q1 double dot t squared, okay? And now we're working back in q rather than x and y, okay? And that distance is going to be equal to L. So we can solve for t here. T squared will be 2L on q double dot, or t is equal to square root 2L on q double dot 1, right? And then, of course, what we would do is substitute this horrible great thing up here into there, which I wouldn't actually write down in an exam. I just point out that we would substitute that thing in, and it would give us t, right? And so we've solved the problem, but it's, you know, we're going to have a fraction under a fraction under a fraction, and then it's not going to get you much further in this problem, so you're kind of there, okay? All right, so there's two interesting things to do in this problem, which is to look at limits. And if I was giving this as an exam problem, for example, I would probably have like a part A, get the Lagrangian, part B, show that the acceleration down of mass little m down the block is given by this expression here. Part C, you know, consider the limit of alpha, convince me that the behavior makes sense. D might be whatever. Okay, so this is more of a in exams the problems are more specified than they are in something like, you know, a tutorial or an assignment problem here, which likes to give you scope to play with it, right? So there's two limits that are interesting. The first one that's interesting is alpha equals 90 degrees. And you can imagine if you take this problem and make alpha equals 90 degrees, then your little mass m is basically sliding down a vertical surface, right? So q1 double dot should go back to g if that's the case. And if you think your way through here, sine of 90 degrees is 1. So this term at the top becomes 1. Cos squared of 90 degrees is 0, so this term in here becomes 0, which means this 1 minus becomes just 1, and so this thing collapses back to g, okay? Makes sense, perfectly good. The other interesting limit to consider is making the mass big M go to infinity. And if that's the case, then that block big M should never move, right? Because you kind of require an infinite amount of energy in order to give it some kinetic energy. And so if we do that, if big M in here goes to infinity, then this term here goes to 0, and our Q1 becomes G sine alpha, which is basically just if we had a fixed block and a block sliding down it, what would be the acceleration, okay? And so you can see that this term in the bottom here exists entirely to account for the fact that the block big M, or the wedge, is able to move, right? And it's a compensating factor on little m in this problem, okay? So it's kind of nice. You can explore some other limits, like what happens if big M becomes 0, what happens if little m goes to certain limits, stuff like that. I'll let you play with those yourself. So at this point, let's take a little bit of a break. 2 problems out of the way, and then we'll come back and we'll deal with another one that's a little more tricky and kind of pushes Lagrangian mechanics a bit further.